In this video, we are going to go over the analysis that we conducted in class, which is simple regression. And in class, we went over two scenarios, using a simple regression with a numeric predictor and using simple regression with a categorical predictor. So let's just go over that a little bit. So the dependent variable in class that we were interested in were people's wages. And as we have discussed, people's wages vary quite a bit. Some people make a lot of money, other people make average levels of money, and others make very little money. And so we want to understand what factors predict people's hourly wages. And so one variable that we selected was years of education, right? So in this scenario, the dependent variable is the hourly wages in US dollars, and the independent variable is the years of education. So let's get started with that. Again, because we have one variable, we're only going to be using simple regression. So to conduct a regression, we're going to go to Analyze, Regression, Linear. We're going to put our dependent variable, which in this case is going to be wage, hourly wage. And the independent variable is the number of years of education. You're going to click OK. And here you have your output. So the output tells you a number of things. A model summary tells you the actual Pearson's correlation coefficient, or measure of association between wages and years of education, which is moderate, 0.44, and positive. R square, if you take the square of this number, you get 0.19, which translates to 19%. In other words, the years of education that a person's have explains about 19% of the variation that we observed in wages. 19%, that's quite a bit. Of course, about 80% of the variation remains unexplained. This ANOVA here, this is a test essentially of the linearity, the relationship between education and wages, and as you can see, is statistically significant. We can assume the relationship is linear. And down here, this is what the actual regression happens. You have your intercept, that is your constant intercept. The intercept is where the regression line meets the y-axis, or a better way to think about it, the intercept is the expected value of y when x equals 0. In this case, it's the expected hourly wage when you have 0 years of education. In this case, you're going to be making negative $1.54, which doesn't really make any sense, but that is what is expected. Next, we have this slope of the regression line, and this slope essentially translates into the effect. What happens to y when x increases by 1 unit, right? And in this case, we see that as x increases by 1 unit, y increases by 0.78, right? Of course, this interpretation lacks nuance because it doesn't take into account what we are talking about. So the best way to report a regression result is to actually talk about it in the units in which the variables are measured. In other words, years of education, the year is the unit, and for hourly wages, dollars is the unit. So a 1 year increase in education is expected to increase your average salary, your hourly wage, by an average of 0.78 or 78 cents. This is the effect, the predicted effect, what happens on average, and as based on this t-test, we see that it is statistically significant given that the p-value is less than 0.05. Moving on to the next scenario, let's use simple regression now with a categorical variable. When you have a categorical variable, interpretation changes a little bit. And the variable that we selected to analyze in class is the effect of gender, the effect of being a female on your hourly wages. And so, but before we conduct this analysis, you need to have an understanding of how gender is measured. So if you go to data view, actually, if you go to data view and you look at sex, you see that 0 is male, 1 is female. To conduct this regression, again, it's the same thing. You're gonna go to regression, linear, and instead of years of education, you are actually going to use sex. You're going to click OK, and again, we get the same tables. This is the Pearson's correlation coefficient between gender and hourly wage, and you see that there's a weak correlation, positive correlation. R squared is 0.33. So gender explains about 3% of the variation explains in hourly wages. Again, it's not as much as hourly wages as years of education, but it's certainly 3%. And you can argue that 3% is 3% too much, given that gender should not explain anything about your income, right? It should not be. It should be completely unrelated from your income. Anyways, moving to the regression table, again, the constant or the intercept is 10.27. Again, the constant or the intercept is the expected value of y when x equals 0. In other words, it is the expected hourly wage when x equals 0. In this case, when you're a male, you're expected to make $10.27. The slope is given to you here, and the slope is negative 1.89. Again, when you have a categorical variable as a predictor, the slope represents the difference between the genders. In other words, again, this is where knowing which variable is 0, which variable is 1, right? So this is the value when x equals 1. In other words, when you're a female. So when you're a female, you're expected to make $1.89 less on average than men. So here, again, when x equals 0, when you're a male, you're expected to make $10.27. When you are a female, x equals 1, you're expected to make $1.89 less than $10.27. And again, this effect, this predicted effect, is statistically significant.